Hello, everyone, and welcome to our live session for today, Wednesday, March 15th. We are happy to be with you. My name is Matthew. I'm one of the instructors and course assistants for our online classes. If you are here with us through that, welcome. If you are here through our other channels, welcome. We are excited to be here. I will hand this over to Professor Impey shortly. We will take your questions. Please post those in the chat. I will grab them from there and filter them. We try to keep them at a level for general public, and I jump around quite a bit to try and give everybody a chance to ask some questions. Chris, if you want to say hello to everyone, and we'll get started with questions.
Okay, welcome everyone. However you found this live stream associated with the online courses, our MOOCs, that we now have 3 of, the general astronomy one, the astrobiology one, and the history and philosophy of astronomy, which is doing quite well. So floor is open for questions on any topic in astronomy.
The very first question is from Charming Leaf, who asks, hi, Professor. Can you describe how stellar nucleosynthesis shapes the universe's chemical composition and how astronomers use it to understand the origin and evolution of elements?
Right, so a big question, because stellar nucleosynthesis is a major topic in astronomy. The theory of it was developed in the 1930s and 40s, and there was a seminal paper by Margaret Burbidge, George Burbidge, Fred Hoyle, and Willie Fowler that was written, I think, in 1959 that really laid out the full physics of how heavy elements are made in stars. And so we've known that now for well over half a century. And it does indeed shape the universe, because stars, including the sun, are making heavy elements by fusion. And the more heavy the star, the more massive the star, the heavier the elements it can create, because the larger temperatures it can create inside its core. And the most massive stars are able to make elements up to iron. Elements beyond that can occur in the atmospheres of giant stars, and especially in supernova explosions at the end of a massive star's life. So you can create all the elements in the periodic table through stellar nucleosynthesis. Sometimes it's a steady process in the core of a star, and sometimes it's an explosive process in a supernova, for example. And the physics of this is very well understood, and the theory is well understood too, and we now have simulations with supercomputers to show how it works in detail. And in general terms, the universe has been creating more heavy elements over its history. When it was formed, a few minutes after the Big Bang, all there was from fusion in the Big Bang itself was helium, a quarter by mass, and a smattering of light elements. There were no heavy elements, no carbon, no nitrogen, no oxygen, no metals. And so all of those were created in stars, and as the universe has evolved and those stars eject some of their enriched elements, because stars mix their elements. Some are trapped in the core, of course, at the end, but some are mixed and then ejected into space. And so the universe has been creating more heavy elements over time and will continue to do so.
Great. It's always a big topic. Next question is from Stan Stachowski, who asks, I have read that some of the experiments at CERN showed data that neutrinos were generated that were traveling faster than the speed of light, and apparently the result was verified through a second collision. Are you aware of this result, and can you comment?
I think I've seen some news stories. I think it's still in the level of unconfirmed, because it hasn't been through full peer review and confirmed independently by other groups, ideally at other accelerators. So I'd call this a tentative conclusion. In the standard model of particle physics, neutrinos are massless particles traveling at the speed of light. So it would be fairly anomalous if they were found to be traveling faster than light. In fact, no particle has ever been seen faster than light. These are called tachyons as a general term. And in fact, if neutrinos had mass, which is indicated by the fact that they can oscillate between their various flavors, then they probably are not even traveling exactly at light speed, but slightly less. So that's what the general theory would predict. So this would be a very unusual result if true.
The next question is from one of our live participants. Sumathi would like to know, what is a supercluster and why is it important?
A supercluster is a large aggregation of galaxies. Basically, the largest structures in the universe are superclusters. So to take the local universe as an example, our galaxy, the Milky Way, is part of a small group called the local group, which has us and Andromeda, and then a few dozen dwarf galaxies. We are falling into the Virgo cluster, which is a large cluster of galaxies, about 60 million light years away, which contains thousands of galaxies, most of which are dwarfs. And the Virgo cluster is part of what's called the local supercluster. This is an enormous aggregation of galaxies that includes perhaps hundreds of thousands of galaxies, again, mostly dwarf galaxies, extending over a distance that's about 100 million light years on a side. So that's about the size of a supercluster. And we found other superclusters through deep galaxy surveys. You need a survey that gives you the position of galaxies and also the redshift to place them in three-dimensional space. Simulations and models of the universe as it expands and clusters and structures form suggest that it's not unusual to have superclusters. And these are not gravitationally bound objects. They're objects that are so large that they're still coming together by gravity, as opposed to a cluster of galaxies, which tends to be a bound object.
The next question is from Pecornin, who would like to know, would it be possible to get close to the sun if the spacecraft had a strong magnetic field surrounding it?
Yes, you could shield a spacecraft in principle that would protect it. The Parker Solar Probe, which is the closest any man-made object has ever got to the sun, was built to withstand enormous temperatures and radiation fields. If humans, now the Parker Probe is just an unmanned probe, but if you actually wanted to have humans near the sun, there are technologies indeed that could provide enough shielding for radiation and cooling, passive cooling, that would keep inhabitants safe. It'd be a very hazardous journey, though. I would not want to do it.
Lawrence K., who's on with us live, asked, "Hi, Professor. How do black holes absorb both, do black holes absorb both dark matter and dark energy?"
Yes to the former and no to the latter. So black holes include dark matter along with normal matter. As they form and they collapse, the dark matter is mixed in with the normal matter. Now, it doesn't interact in the same way. Normal matter interacts through electromagnetic forces and dark matter doesn't. But it does have gravity, of course, because dark matter particles have mass. And so black holes will contain dark matter as well as normal matter, and they collapse, including both types. Dark energy is different. Dark energy is a property of space-time itself. And so a black hole is a fairly small, localized object in space-time, and so there's no particular component of dark energy in a black hole.
So the next question is from Hernan Reyes, who's on with us live, but also sent an email question regarding Carbonaceouschondrites, these asteroids and meteorites. The question is, if the idea that carbon-rich asteroids brought material to the Earth, could it provide some support for the argument that life could be unique to our solar system if there were carbon materials brought, but not necessarily like amino acids?
The issue of where the amino acids or the building blocks of life came from is still under debate. It's certainly true that Carbonaceouschondrites have amino acids. The Murchison meteorite, which fell in Australia decades ago, had 50 different amino acids included in it. And I think the total of amino acids that have been found in Carbonaceouschondrites is up to about 500 different amino acids. Life on Earth, of course, only uses 22, and then 2 more occasionally. So it's a rich source of amino acids. However, the Miller-Urey experiment showed how amino acids could form in sort of prebiotic early Earth conditions quite naturally without any assist from objects coming in from space. So essentially both ideas have to remain on the table, and they both may have been important. If amino acids and building blocks form naturally, then there's no reason why the Earth should be unique in hosting life.
Excellent, thank you. And I think you answered the question better than I asked it. So thank you for taking care of that for me. I appreciate it. The next question is from one of our live participants who would like to know if you are able to still find time to stargaze in your spare time, and if so, when and where do you do that?
Not as much as I'd like. I don't live in a particularly dark place. I live in the foothills of Tucson in a suburb where there's a fair amount of city light. Not a lot of street lights, but there's a lot of city light. It's not a very good place to do stargazing. I have a neighbor and friend, Irene Kitzman, who often is online with these live sessions, and she has a telescope in her backyard just 50 yards away from me, and so I've observed thanks to her. She has a telescope on a dark side in Portal as well. So no, I don't really do as much stargazing as I used to. And of course my research always involved huge telescopes located in Chile or thousands of miles away, and that's not a trip you make very often.
Faisal, who's on with us live, would like to know, has it become possible to control satellites? For example, is it possible to control and change it from an equatorial orbit to a polar orbit? Like, can we move satellites around in space, or is it once they're up there in an orbit, they're just stuck?
Satellites are generally built to purpose, which means they are designed and constructed for one orbit, one type of observation, which is to say they don't essentially have propulsion mechanisms on board. They're not rockets in any sense. So once a satellite is put in orbit, there's very limited abilities to move it or move it to another orbit at all. Maybe to slightly adjust it. It is certainly true that some very large satellites have small retro rockets included, as gas jet rockets that allow it to adjust its trajectory in its orbit, but these are modest adjustments, nothing dramatic like changing from a polar to an equatorial orbit.
Excellent, thank you. The next question is from Stringing, who's on with us live. If the single point Big Bang has been displaced by the everywhere all at once theory, is that theory still the preponderant theory, or are there competing theories to the single point theory of the Big Bang?
Well, the main competing theory, or variation really, on the Big Bang theory is the multiverse idea, which is the idea that the Big Bang as a singularity in a point in space and time from which everything around us emerged was not the only event. I mean, causally there could have been other space-time events leading to other universes with different properties, and that's the multiverse idea, which does not have direct experimental support. So I wouldn't call it a rival to the Big Bang itself, because it sort of embeds the Big Bang idea. It just extends it to other possible universes.
The next question is from JP. Due to its precession, it's said that the pole stars keep changing. So is this a repeating cycle of stars taking their position as pole star? Do we know how many years it will be before Polaris loses its position and then comes back?
Yes, the precession of the Earth, as it spins, the Earth has a wobble, and that wobble of 23.5 degrees, that's the orbital tilt, and the precession period is about 24,000 years. So the North Pole of the Earth will only be pointing at Polaris for a period of time, and will gradually migrate away, and then after a few tens of millennia, the pole star will again point at Polaris. We've seen evidence of this because one of the Greek pyramids, the Great Pyramid of Cheops, has a sighting line. It was the path the pharaoh's spirit was supposed to have taken into the sky, and if you follow that sight line now, you don't see any bright star in the sky. But if you wind time back to when the Great Pyramid was constructed about 4,000 years ago, the bright southern star Thuban was at the end of that sight line. So that's very direct evidence that the precession happens, the migration of the stars, and that it was built into some of the archaeological structures of ancient civilizations.
Excellent. The next question is from one of our live participants, who would like simply to know, Vikrant would like to know, what is redshift?
Redshift is recession velocity. It's the phenomenon where, in the cosmic sense, galaxies are all moving away from us, carried by the expansion of space-time. And so as space-time expands, photons traveling through space-time are stretched, literally, by the space-time expansion. And as their wavelength is stretched, that means it goes to longer wavelengths, lower energies, redder. And so the redshift of galaxies is literally a function of expanding space-time, where the light traveling through it has its wavelength stretched. And the more it travels, the longer it travels, the more the redshift. So redshift increases with distance.
The next question is from one of our live participants. John V would like to know, if the universe is expanding, how can two galaxies collide? So, for example, the Milky Way and the Andromeda galaxy in the future. Can gravitational force overpower dark energy?
Yes. So the universe is generally expanding, and that's just the large arena of the universe. Space-time everywhere is expanding at an accelerating rate due to dark energy. But within that space-time, galaxies, of course, feel gravity, the mutual gravity of other galaxies. And if that mutual gravity is strong enough, then it sort of exempts those galaxies from the overall cosmic expansion. And Milky Way and Andromeda are approaching at 100 kilometers per second because they're close enough and their gravity is strong enough to exempt the pair of them from cosmic expansion. And clusters of galaxies are in the same category. They are galaxies that stay in one region of space orbiting each other, and the cluster does not expand with expanding space-time because it's a bound object. The mutual gravity of the galaxies keeps it intact and at roughly the same size. So the expansion of space-time is true on the global, on the largest scales, but on smaller scales, the gravity of objects in the universe can mean they don't have to expand or move away from each other.
The next question is from Vikrant, who would like to know, are wormholes complex masses of dark matter? And if so, is their gravitational field as exponential as black holes?
We don't know if wormholes exist, and if they did, it's not obvious they have anything particularly to do with dark matter. Dark matter is just the variation on normal matter that seems to be more abundant by a factor of 5 or 6 than the normal matter that we're made of. Black holes will contain dark matter, and wormholes are just a hypothetical object that we've never observed, but there's no particular reason to invoke dark matter to explain wormholes or to predict wormholes.
Bakornin would like to know, are there particles in the standard model that fill no purpose, that we don't see very much or don't seem to do much of anything?
Well, the standard model does have some issues with it, even though it's an excellent description of particle physics. The classic example is the muon, because a muon has a mass, of about 200 times an electron's mass, whereas protons and neutrons are 2,000 times. And when this muon was discovered over half a century ago, a famous particle physicist, I don't remember who, said, "Who ordered that?" Because it was just not obvious why a muon would exist as an intermediate mass between protons, neutrons, and the very light electron. So that is a story of the standard model. The standard model does not explain why all the particles have the masses they do, or why there are 3 generations of particles. And so there are definitely things that the particle model we have, which is very successful in explaining properties, it doesn't predict or explain everything, including intermediate mass particles, very high mass particles that have very short lifetimes. There's many of those that are produced in accelerators. And we know the standard model is not the final story of particle physics.
The next question is from one of our participants who's online with us, Stalling Claw. How do astronomers use transit methods to find exoplanet composition and mass?
Well, the transit method is the one that's been used to find the majority of exoplanets at this point. The census is over 5,300, and more than half of them found by transits, and most of those found by the Kepler satellite, which is no longer functioning. In a transit, the planet passes in front of the star and dims the star slightly, and so that's how the planet is discovered, by an eclipse or a transit, and that gives you the size of the planet and its orbit. However, the starlight is also passing through the planet. It's being blocked by the planet's body, but if the planet has an atmosphere, then the starlight is filtering through the atmosphere of the exoplanet as it transits. And so you can do a clever spectroscopy technique to look for absorption lines or chemical signals imprinted on the absorbed light of starlight filtering through the exoplanet atmosphere. And your control experiment is, of course, eventually the exoplanet will be on the far side of the star, and so you can measure the starlight without the exoplanet in front and then with the exoplanet in front and do spectroscopy both ways. And this will tell you the chemical composition of the atmosphere of the exoplanet. It's a very powerful technique. It's only been used for about half a dozen cases, but probably dozens more are coming.
Wendy Travers sent an email and would like to know, can you please explain how spontaneous symmetry breaking works in regards to the Higgs boson?
So the Higgs boson is a part of the standard model of particle physics. It's the final piece in the puzzle, if you like, of the standard model of particle physics. Spontaneous symmetry breaking is not directly related to the Higgs, because the Higgs is a field, and the Higgs is a field that is presumed to permeate entire space, the entirety of space, and the property of that field gives rise to the mass of the particles moving through it. And that field operates in a way that doesn't have anything directly to do with spontaneous symmetry breaking. Spontaneous symmetry breaking is more usually invoked in terms of unified theories of particle physics, which try and unify all the forces that have quite distinct properties at low temperatures, but at high energies they recover the symmetry of a superforce, and then that symmetry is broken at lower temperatures.
The next question is from Adrian, who asks, stars have been found older than the age of the known universe. Do you think they could be left over from previous universes?
I think that's not actually true. I think there's errors attached to the measurement of star ages, and to my knowledge, no star has been found that's older than the 13.8 billion year well-measured age of the Big Bang. The age of the universe through the Big Bang model is fairly accurately measured, maybe a couple of percent. The age of old stars is a much less certain method. It's a tricky thing to do, and I don't think the errors are much less than 10% ever. So that means a star that may seem to have an age of 13 or 14 billion years has an error of about 1 billion or 1.5 billion years on that age measurement. And so I think that means stars have been found that are close to the age of the universe, but none that are definitively older than the universe, which would actually violate the Big Bang model. That would be a deal breaker for the Big Bang.
Attila would like to know, dear Professor, why don't we send another message to the universe like the Arecibo message?
Well, astronomers are working on messages that they want to send. This activity is called METI, Messaging Extraterrestrial Intelligence. It's a relative, of course, of SETI, the Search for Extraterrestrial Intelligence, which is listening for signals. I'm on the International Advisory Group for METI, and as a group, we talk about what kind of messages you would want to send, what kind of facilities you'd use to send them. Since the Arecibo message, very few messages have been sent. Of course, Arecibo had a catastrophic failure a few years ago and will not be rebuilt. Meanwhile, the Chinese have built the FAST, Fast Radio Telescope, which is bigger than Arecibo, which was only 305 meters. FAST is 500 meters across, and FAST is intending to do a messaging experiment in the next year or two.
Can you talk a little bit about the challenges of sending those kinds of messages? Why don't we just do it all the time? Why isn't there a radio telescope that's just beaming messages out frequently? Why do we have to have such, infrequent communications?
It's a good question. I think there's several parts to the answer. I mean, one is that radio telescopes are in high demand. Radio astronomy is a big field. People use radio telescopes to do cosmology, to study star formation, to do all kinds of astronomical science. And so METI, Messaging Extraterrestrial Intelligence, is a niche subject that is never going to get the majority of time on any telescope unless it was purpose-built for that activity, as the Allen Array in California is built for the SETI experiment. That's one answer. And the other part of the answer, of course, is that to many scientists and many members of the public, it's a kind of a shot in the dark. It's a very much a long shot because the objects you're sending messages to may not have life on them. The travel times are millennia and far more than the age of an average human or even our civilization, so the prospect of getting an answer is very low. So it doesn't seem like a very practical experiment, and I think it gets criticized on those grounds legitimately. So for that reason, it's just never going to be a dominant idea. If some rich industrialist or philanthropist chose to fund a radio telescope just to do METI, then it would get a big leg up. But at the moment, it just has to fit in and get a toehold on telescopes that are used for many other types of science.
Thank you. Ellensburg, Washington asks, what do we expect to learn from a mission or the mission to Titan?
Well, the Titan mission is extremely exciting because remember, it's a long time since we've been back there. The Cassini mission, of course, made very important observations of Titan and a dozen or more close flybys. It also dropped the Huygens probe, but that was 2005. That's a long time ago, almost 2 decades now, and only sent back about half an hour of data from the surface. So that whetted our appetite, but it's been an awful long time since we got to go back. The mission that's now planned by NASA is exciting because it uses fairly recent drone technologies. So we're going to send drone-type technologies to fly inside the atmosphere and to dip into, to hover above and sample the ethane-methane lakes. Remember, Titan is an atmosphere that's actually at the base denser than the Earth's atmosphere. So flying drones on Titan is just like flying them on Earth. It's much easier, for example, than the helicopters that were flown on Mars with a very thin atmosphere. That was extremely challenging. So the Dragonfly mission that's planned is an extremely exciting mission, but it's about a decade before we're going to get that kind of data.
The next question is from Hernan, who has a second asteroid-related question. NASA has an ongoing mission called OsirisRex to bring back samples from Bennu. Can you talk a little bit about how Bennu was chosen and how common those kinds of carbon-rich asteroids are in our solar system?
Carbon-rich asteroids are, I think, a simple majority of the asteroids, so they're fairly common. The choice of Bennu was a difficult choice because this is a mission that is, in total a decade in the planning, the execution, and the sample return, which will happen next year. And the distance involved is prodigious. So Bennu was chosen because it's an Earth-approaching asteroid or an asteroid that comes well within the asteroid belt. We would not attempt a mission to the asteroid belt. So Bennu was chosen to be the right chemical composition or geological composition based on reflectance spectroscopy done ahead of time. It was chosen to be reachable by a space mission on a reasonable time, which is to say a few years each direction, and there's not that many asteroids. And it was also chosen to be large enough that the Bennu collection strategy would work. If you have a very low mass asteroid, a very small asteroid, then the gravity of it is essentially negligible. So the way of getting a sample becomes extremely difficult. It was hard enough with Bennu with its weak gravity. So all of those things put together really lowered the pool. There was a long selection process that winnowed down from, I think, a list of 100 down to a few dozen, then to a handful, and a lot of planetary scientists were involved in the selection, not just the people who did the eventual mission.
Jeffin Raja has a question about the velocity of light. How do physicists predict that light has moving velocity? And what is the standard experimental method to measure the speed of light?
Well, the prediction of the speed of light from theory comes from Maxwell's equations. So the electromagnetic theory that James Clerk Maxwell produced in the 1870s, so 150 years ago, includes a constant, and the equations all have a physical constant there, which becomes little c, the speed of light. And it's measured experimentally to be almost exactly 300,000 kilometers per second. So the prediction of the speed of light and its universality, it all comes from Maxwell's equations.
Rafi would like to know, will we see different constellations in the sky after billions of years from now?
Oh, definitely. The constellations will change on much shorter times than that, because remember, the stars we see in the night sky are mostly in the nearby parts of the Milky Way, distances of tens to a few hundred light years. There's some that are a few thousand light years away, but most are hundreds of light years. And that's a nearby part of the galaxy, and all the stars around us are, of course, moving in a big circular orbit of the Milky Way and the disk that takes 250 million years, but they also have random motions on top of that. And those random motions will, over time, where that means millennia, move them substantially on the sky. And their brightnesses will change and their positions will change. So the constellations that we know now will be scrambled in a few centuries, and by 1,000 years will be unrecognizable.
Next question is from Kurt, who asks, who would you consider to be the greatest astronomer before the era of telescopes?
Well, that's usually an easy call because Tycho Brahe gets the nod. He is, essentially known as the greatest naked eye observer. So before the invention of the telescope, there were many people, of course, who observed the sky, but everyone has a naked eye and they can do, what they want with it. Brahe took observation with the naked eye to a whole different level. He was funded by the King of Denmark to build the Uraniborg Observatory, which is on the island of Hven, H-V-E-N, which was owned by Denmark. Now it's owned by Sweden. And on this island, he built an observatory and for over 20 years made careful observations of the planets, especially Mars. And he was just using setting circles and octants and various sighting mechanisms because he had no telescope. And his observations were no better than anyone else could have done, but he applied himself carefully to the measurements. He improved the accuracy, and he made them over many years, and so he beat down the errors by just persistence and perseverance.
Dennis has heard that redshift has been described as analogous to the change in pitch in the sound of a siren as it approaches you and then passes your position. Is this an accurate analogy for light?
It's a good analogy for the Doppler shift. So we can, if we consider the Doppler shift, and that mechanism and idea was from a German physicist, Christian Doppler, working in the 19th century, then yes, we can have redshift. So a source of light that has a relative motion to us, if it's moving away from us, the waves are stretched away in the direction of motion, and that means a redshift, longer wavelength. And if the light source is moving towards us, it sort of squashes the wave fronts in the direction of its motion, and we see a blue shift. So that's the redshift and a blue shift in a Doppler shift setting. The redshift in cosmology is a completely different mechanism, and they're often confused, but they shouldn't be, because cosmological redshift is the expansion of space-time itself, and so it's nothing to do with relative motion, like with a siren changing its pitch. So Doppler shift applies to light waves or sound waves, any kind of wave.
The next question is from Sarb Sand, who sent an email. Why do we get tides on the opposite side of the Earth in addition to the side facing the moon? Seems to me that we should get tides only on the side facing the moon due to its gravity.
Right, so the tidal force is basically a stretching force. So the way to think of it is that the gravitational force between any 2 points depends on the distance between them and the mass of the 2 objects. So we're talking about the moon and the Earth here, so those are the 2 masses. But if you're talking about the distance, then the moon is closer to the near side of the Earth than to the far side of the Earth. So it has a stronger gravity force on the near side of the Earth than the far side of the Earth. And so that amounts to a stretching. And if you think of it that way, the moon is exerting a stronger force on the ocean that's in the direction that's towards the moon than the ocean on the far side of the Earth. And so that stretching applies to the bodies of water too. And so you have a stretching force that applies in opposite directions, and as the Earth rotates, that creates 2 tides a day.
The next question is from Shireen McKenzie. What discovery are you anticipating and or eager to see over the next decade?
Well, the biggest one, of course, would be the detection of life beyond Earth. I think a decade is about the right time scale for that to happen. I don't think it will happen in the solar system because the missions to do life detection are difficult, expensive, and they tend to take a long time. So I don't think any of those missions will happen in a decade. It's possible that with sample return from Mars in about a decade, we might find evidence of fossilized microbes in some Mars rocks. That would be the only chance I see in the solar system. The more likely scenario is that we do the sniffing of exoplanet atmospheres with the James Webb Space Telescope now, and with very large ground-based telescopes being built, including the one we're building in Arizona, or building in construction down in Chile. The mirrors are built in Arizona. So there's 3 huge telescopes that are under construction. They will all take data in the next 5 or 6 years, and they are all going to try and look for evidence of life on exoplanets by alteration of those exoplanet atmospheres by microbes, as happened on the Earth with the creation of the oxygen we breathe.
The next question is from Faisal, and it's a 2-part question, so I'll split it up. Is it true that the Sun is classified as a 3rd generation star?
I'm not sure it's formally a 3rd generation star. I mean, this classic designation of astronomy for star types is population 1 and population 2. Population 1 are the younger stars that have been formed in the last few billion years. Population 2 are the older stars that formed when the galaxy formed. And then population 3, the 3rd population, is of a hypothesized initial, very early generation of stars soon after the Big Bang, basically the first stars to form. Well, in that context, the Sun is 4.5 billion years old, same age as the Earth, and so that would place it as somewhere between population 1 and 2.
And so then her second question is it possible, or to what extent is it possible, that there would be planets capable of life revolving around the earlier generations of stars, the 1st or 2nd generations of stars?
It is possible. Basically, I mean, heavy elements are not existent in the universe until the first stars form. All you have is hydrogen, helium, and a very few light elements. But almost as soon as you have star formation, those massive stars are making heavy elements and spitting them out into space. And you sort of have to model the chemical evolution of that and how long that will take to build up enough heavy elements to make planets and life. And the best guess is it could well be less than 1 billion years. So it's entirely plausible that in the first billion years after the Big Bang, which is a long time ago, over 13 billion years ago, the life formed and the Earth-like planets existed. And so that's what we think, and so it's certainly worth looking for very distant planets, Earth-like planets, using indirect methods, because we think planets could have formed very early in the history of the universe.
The next question is from Wendy, who sent an email. If the Higgs field were to undergo a phase change of some sort in the future, how would life be affected?
Well, if there were a true phase change in the Higgs field, that would be sort of catastrophic or very dramatic, because the Higgs field is what gives particles their mass. And so if in some way the phase change and the coupling of the Higgs field to the mass of particles in the Standard Model changed, then their masses would change, and all bets are off, because if the mass of fundamental particles, protons, neutrons, or their constituent quarks, changes, then the properties of those particles, their ability to form stable entities and molecules and so on, would be thrown completely into doubt. So I think that would be a potentially catastrophic thing to happen.
The next question is from James. Does the simulation hypothesis recognize and accept the existence of the physical universe? And if it does, how does it explain the infinite ways in which there is physical contact with humans?
Yeah, the simulation hypothesis definitely is posited in terms of the universe we know. It's basically saying that within the universe we observe and have measured, there could or should be intelligent entities that have developed the ability to simulate other living entities. And at that point, you become unsure whether you yourselves or your civilization is a simulated entity or a real entity. Now, the whole thing could just be a shell game, and then there is nothing other than the simulation. There's no physical universe. But the simulation hypothesis does not demand that. It can be started by talking about a physical universe where within that the technology to do simulations exists and develops to a very high level.
Sarah, who's on live with us, would like to know, do we still think there could be a 9th planet in our solar system? And if it exists, why haven't we found it?
The search for Planet 9 does continue, but I would say that it's winding down. The obvious, any planet of Pluto's size or larger would not evade the current surveys that are looking for Kuiper belt objects, essentially. So the Kuiper belt is between 40 and 80 astronomical units, or Earth-Sun distances. And those surveys are sensitive to Pluto size or mass and even smaller. So hiding a Planet 9 that's Pluto mass is getting very difficult now. I would say almost impossible. And those surveys are going to wrap up in the next couple of years. There definitely could be other smaller planets out there, dwarf planets, and that wouldn't be surprising at all.
The last part of her question was hypothetical, but we can talk about it more generally. So the question was, could a hypothetical ninth planet be made out of dark matter? But then the more general question is, could there be massive objects made entirely of dark matter?
So the possibility of dark matter only objects is a real one, and astronomers, but not for planets. I think planets are objects that are the debris, the leftover effect of star formation. They're made mostly of rocky material and heavy elements. And so, planets are unlikely to contain any significant amount of dark matter. But on the largest scales of galaxies, which are dominated by dark matter, as the Milky Way is, and dwarf galaxies in particular are very dark matter dominant. There are some that are, as opposed to the normal ratio of factor of 5 or 6, there's some dwarf galaxies where the dark matter is 10 or 20 times the amount of normal matter. And so there have been a few galaxies found that are almost devoid of normal matter and are pure dark matter halos. And that's not completely unexpected in terms of simulations and cosmological models. And it's very interesting for astronomers to look for such objects because they would represent extremely inefficient places for star formation, because it's suggested that the point is not that these dark matter dominated galaxies have no normal matter. It's just that normal matter is very cold and gaseous and has never formed stars. And the question would be why.
The next question is from Yogesh Bang, who asks, what can we expect from gravitational waves to reveal in the future?
Well, gravitational waves is a booming field, of course, with the success of LIGO. And LIGO's recent upgrade in sensitivity, it's now in production mode, and very soon will start returning, we think, about 1 black hole merger a week. So very high event rate compared to the 24 roughly that it's found since 2016. There are other gravitational wave detectors on the horizon. There is one in Europe. Japanese have one, the Indians have one, and there's another few under construction. So we're eventually going to have, quite soon, in 3 to 5 years, a worldwide network of gravitational wave observatories that can work in concert with much higher sensitivity, and especially much higher directional sensitivity than LIGO alone, for example. So we're entering a golden age of gravitational wave astronomy, including the development and deployment of an interferometer in space to do what LIGO does for massive black holes as opposed to stellar mass black holes.
The next question is from Drishti. Do we expect or hope to see any discoveries regarding black holes in the coming few decades?
Well, there's a lot of black hole physics that we would like to get to grips with. I think we're going to learn more about the detailed properties of black holes. The work on the galactic center black hole will increase as we get better observations of stars. Perhaps we'll see stars disrupted or even consumed by the black hole. We'll have increased tests of general relativity near the event horizon of that black hole. I think we'll learn more about the feeding and fueling mechanisms of supermassive black holes, the ones at the center of galaxies. And we'll learn potentially about the information paradox. We'll potentially resolve with theory rather than observation some of the conundrums with black holes, including the fact that they have singularities, which essentially breaks general relativity, and the information paradox, which is that information is lost inside a black hole, but according to quantum theory, it shouldn't be.
We have kind of a philosophical, religious-related question from Nash Onadero. Science helps us understand some mysteries in nature, but how can we explain astronomically some historical records or biblical stories or stories from religious texts such as ones where the sun stood still and the moon stopped for some time in the past? How do we deal with those?
So I'm not an expert on this. I've read articles, of course. So astronomers and theologians have collaborated on looking at biblical texts and ancient texts. And it's very tricky to interpret these texts. Sometimes the descriptions are not contemporaneous. Sometimes the descriptions were written down a long time later, generations later, or years later. And so you have a problem there. These are not direct observations in the way we think of direct observations. They're passed down over time, and things can get lost in translation. The other thing that's obviously happening in religious texts is there's a high level of the use of metaphor and analogy and evocative language that isn't simply descriptive in a scientific sense. So when there can be a reason why the Earth stood still or the moon stood still, that doesn't actually reflect the fact that their motion ceased. But there is a niche of astronomy that looks at biblical texts and tries to look at astronomical events. A big prominent example is the Star of Bethlehem. So the historical figure of Jesus, there was an omen, a telltale of his coming, which was the Star of Bethlehem, and there are astronomers who've made moderately convincing arguments that there was a supernova visible in the daytime sky and about the right part of that world and about the right part of the sky. And so that was an astronomical event that then worked its way into the Bible. And there are a few other instances of that, but it's very difficult work because we simply don't know the intention of the people writing these texts. They've been passed down many times, and they're using very lyrical and metaphorical language, not literal and scientific language.
Excellent, thank you. The next question is from Supreme Scientist. Hi, Professor Impey. I have a quick question. I'm 45 years old. Would I be considered too old to pursue a career in astronomy?
Well, it's hard to do astronomy starting in middle age because, the amount of training is substantial. You have to basically have a bachelor's degree in physics or astronomy, and that's 4 years, say. And then you have to do a PhD, which is 6, maybe 7 years. So that's a decade. That's 10 years right there. And so starting from scratch, assuming you didn't have credits from another college degree that mapped into physics and astronomy, you're talking about a decade. And then getting a job in astronomy, of course, that's challenging too. People who come to astronomy later in life tend to become very avid amateur astronomers, and that can be just as fulfilling as a professional career because the tools of the amateur astronomer are not so good. Their telescopes, approach a meter in size for some of them. They have CCDs, the same tools that astronomers use at the back end. Some of them are even cooled with nitrogen. That would be extreme, but certainly photoelectrically cooled. So they're very sensitive, and you have a dedicated observatory. You're not sharing your time with other people as the telescopes that we use are. So there's something to be said for being an avid amateur astronomer, because the path to professional astronomy for middle age is quite a long and arduous path with no guarantee of success, of course.
That's great. And I also just wanted to mention that I have several friends who don't even have PhDs and work in astronomy. So there might be another avenue there as well. So you could become you could do signal processing or, instrument design, and some work in astronomy could be done, without necessarily getting a PhD. The next question is from Drishti, who would like to know, what is the difference between a neutron star and a quasar?
They're quite different scales. They're entirely different scales. A neutron star is the remnant of a massive star after it dies. When it loses some of its outer envelope and the core collapses to a state that amounts to nuclear matter. It's the same state as the atomic nucleus, only a much bigger mass. And that's an end state of a star. It does not shine at that point. It's pure neutron material. And the subset of neutron stars that have glitches or have particular atmospheric properties give rise to pulsars. A quasar is a totally different scale beast. We think quasars are supermassive black holes at the centers of galaxies that are fueling on gas and stars near the centers of those galaxies and ejecting material along their polar axes and accelerating particles and jets and putting out emission across the electromagnetic spectrum.
The next question is from Arunabha, who asks, as we are looking forward to colonize and terraform other planets, even if we can terraform the atmosphere to our needs, how do we compensate for the difference in gravity on those planets or moons?
I don't think we have a path to change the gravity of a planet. So terraforming Mars, which has been considered for half a century or more, quite seriously by NASA, for example, not just by space visionaries of various types. Yes, there are pathways to terraform Mars to gradually give it an atmosphere and oxygenate it with microbes. But the gravity will always be that low gravity. And I don't know of any way that you can change the mass of a planet. That's an undertaking that you can't really consider. So whatever we do in terraforming or inhabiting other bodies in space, we will be stuck with the gravity. And that's kind of bad news, because the only planet in the solar system with essentially the same gravity as the Earth is Venus, which is really uninhabitable. There's no way we can make that habitable.
The next question is from JP. Starlink is sending thousands of satellites into space for high-speed internet service. What are the impacts of this congestion? How does it affect astronomy?
It's a big issue in astronomy, and astronomers are alarmed and trying to do something about it, but have limited power. Astronomers don't have any clout over commercial entities like SpaceX or others who are gaining money from telecommunications and so on. Their economic model does not really accommodate astronomers. So there was recent papers on this because of the concern that these new deep telescopes we're building were going to have almost many of their images messed up by the increasing number of satellites. And what was found in the very recent paper is that the amount of the fraction of images that are contaminated by streaks from these satellites has gone up over the last 5 or 6 years from 3 or 4% to 6%, so almost doubled. But 6% is still only 6%. So it's not like every image from major telescopes is messed up by this. And it's particularly dominant, the effect is dominant at dusk and dawn in the middle of the night. That's just due to the orbits of the satellites and them reflecting sunlight. So it is a problem, it is getting worse, and there's unfortunately not that much astronomers can do about it.
The next question is from Nitish Kumar. If extraterrestrial objects or organisms are ever discovered, do you think they would be made up of elements that are not present on our periodic table?
No, I think they'll be common to our form of life. So it's been said that chemistry is universal. And by that, it means that we've looked far off in the universe now to distances of 12, 13 billion light years, and we see the same chemical elements out there back in time and far away in space that we see here. There's been no discovery of any chemical element that isn't in the periodic table in the last century of observation. So we're pretty confident that chemistry is universal, that objects will have the same elements far away in space and time, and therefore, if carbon-based chemistry is a mode towards biology, then that path will also exist elsewhere in space.
And then kind of a follow-up question to that is, what about something like new minerals? Science fiction loves to invent new minerals that are made of elements that we understand, but put together in new combinations. What do you think the odds are that something could be some kind of novel mineral that exists out in space that we haven't discovered?
There are certainly the possibility of mineral types that we haven't seen on the Earth. I mean, terrestrial geology is a particular kind of geology. So if you had planets that were subject to that had different levels of gravity or different stresses or forces, or had a slightly different initial chemical composition, you could definitely imagine different mineral forms. And the mineralogy of the Earth is interestingly connected with biology itself. So in the history of the Earth, before there was any life, the number of mineral types was, I think, only a few dozen, maybe 100. Well, it was fairly modest. When life formed, the interaction of biology and chemistry and mineralogy led to the creation of new minerals. So life is essentially processing elements. I'm talking about microbial life here, because this is billions of years ago. And so the Earth now has hundreds of different mineral types. I think it's over 1,000 actually. And so that's going to be a typical number. And do we have all the unique Do we uniquely have all the mineral types that exist in the universe? I'm sure we don't. And so it's quite plausible that there are novel or strange or unusual mineral types that are not on Earth.
The next question is from Ryan Weber, who asks, if you travel close to the speed of light, time will pass more slowly for you. Does that mean that as you look at the universe, or out at the universe, that it would be playing fast forward from your perspective?
Not necessarily. If you travel at close to the speed of light, then your clock, as seen from an outside observer, is traveling slower. But the universe has its own clock, and its own clock is driven by stellar processes, by the expansion of the universe. And so that clock is not changing. It's just a very localized phenomenon due to your immediate travel.
Pecornin asks, do scientists look for evidence of artificial life or mainly biological life when they're looking at life on exoplanets?
I think at the moment, scientists look for life as we know it. So, I mean, that's the simplest thing to do. When you don't know how strange or bizarre or unusual biology might be elsewhere in the universe, you look for the thing that you can recognize and identify. So we're looking for life as we know it. Life based on carbon chemistry, nucleic acids, some sort of a replicating molecule, if not DNA or RNA. As soon as you go beyond the realm of normal biology and its variations to artificial life, then you simply don't know what you're looking for. So the problem is not that artificial life might not exist elsewhere in the universe. The question is, how do you define it well enough to know what to look for? That's a classic problem in science, and it's not really been solved. So for that reason, scientists don't tend to look for artificial life.
Ellensburg, Washington would like to know, Pluto's moon Charon orbits around Pluto, and it seems that Pluto is also circling around some kind of invisible spot along with Charon. What could that invisible spot that they're orbiting around be?
Well, there's a fair amount of evidence that there are small companion moonlets in the Pluto-Charon system, and so that would cause them to move about a point that's not just the midpoint or a vector point between the two main moons, and I think that's the best explanation there. These systems this is very far away, billions of miles, and so it's very hard to see small moonlets at that distance.
Yogesh asks, most of the stars in the universe are binary stars. Is it possible that our sun has or had a companion?
It's possible, but clearly if it did have a companion, they separated, or there was an ejection event very soon after formation, because there's no sign of the companion at the moment. But it's certainly possible that the cloud out of which the sun formed another star nearby, and they interacted with each other and then parted ways. But the evolution of the solar system and the formation of the planets speaks to having occurred in a single star system.
All right, it is 11 o'clock, so we are wrapping up this. We're going to have one final question, and then we'll wrap up our live session for today. For those of you who are still with us, make sure that you like and subscribe to our videos and our channel, and click that bell icon so that you can hear about future live sessions. Thank you so much for having us today, or being with us today. The final question is from Adrian Murray, who would like to know, could we be living inside of a black hole and our whole existence in universe is actually inside a singularity?
Well, at some level, people have analogized the horizon of the universe, the distance, the limit we can see, to an event horizon of a black hole. But there's really quite substantial differences. A black hole event horizon is an information membrane. It's a region, defines a region from which no information can escape, and it's also a situation of a very high density of matter. The universe itself is a very low density object, and the horizon, the limit of our vision, is not really analogous to an event horizon. It just represents a limit to the space we can see given the finite age of the universe. So I think the sort of general talk people make about us living in a huge black hole is not really accurate. It's not really black hole physics. but it's an interesting thing to consider. So thanks for all those questions, and I'm not sure if we have the next couple of sessions scheduled, but we'll talk about that and put those dates up to plan ahead a little bit. But thanks for the questions today, Matthew, for facilitating, and we'll be with you in a couple of weeks.
So Chris, you're right, we do not have those scheduled, but if everybody, if you scroll to the top of the chat, there is a link to our Google Calendar. You can subscribe to the Google Calendar, and when the new sessions are put on the calendar, you can view them there. We'll also send them out through the course email systems. Thanks, everybody. Take care.